Greetings everyone. I want to go over the homework from 11.5. So the first one was this big graph, and we had to do it. This number 4 asked to use the PRIM algorithm. And then the other exercise is Kruskal, so that we have seen both in action. Okay, so the way it goes here is, remember, what we need to do is we pick edge that is adjacent to what we have already have. Of minimal cost, I'm going to say cost, and very important, without making a circuit. Because we want to build a tree, so we can never make a circuit. So we have to pick any edge, and the two things is it has to be minimal cost. Well, three things. It has to be adjacent to what we already have. It has to be minimal cost, and it is without making a circuit. Those are the three conditions that we constantly have to be on the lookout for. So, okay. And of course, when we start, there is nothing yet, and so we can pick whatever we want, and we have to pick something, of course, of minimal cost. So I'm going to make, let me perhaps see whether it makes, can change my paper here. Okay. So, so here will be the edges, and here will be the cost of these edges. So I'm start with, just for simplicity, I'm going to start on the left. So this is going to be my first one, so that is AB, and that has cost 1. So what can I do now? Well, there's a lot of things that connects to it. I'm going to look first, is there anything of, you see here, the costs are the 1, 2, 3, or 4. So let's go from lowest to biggest. Always see, is there anything of cost 1 that I can use? Yes, there is at least, I see at least one, and I'm not going to try to be smart and find another one. At the moment I have something, I take it. AE, cost 1. Is there anything of cost 1 that I can add to this green thing? I don't think so, right? The only things that I have are cost 2 edges. I'm going to take one of those. I'm going to take one of the curved one here, just for the fact, something to do something else. So I take AM. You see there's going to be many different ways of doing this. Cost 2. Anything of cost 1 that attaches to this? Nope, I didn't create anything more. So I can do another cost 2. I can take it, I'm going to take it here for just to do something else here, BC. Just to show you that you don't have to continue with the branch or whatever it is that you're constructing. Okay, now I chose this one because now I have another option of a 1 here. So in this case I have no choice, there's only one left. There's only one of cost 1, that is the CD. So I have to take this one. So CD as cost 1. And this in turn gives me one option for another cost 1, that is DH. Okay. I'm arrived at a situation, I think, where again, in fact, all cost 1 are used. So I have to work now with cost 2. Perhaps not. But there's a couple of them. Let's rule out. Let's see what we can rule out already. Like for instance, this has to be ruled out now, but this would construct a circuit. Okay. At the moment, I don't think anything else is really ruled out. So I'm going to take this. I said I had to take one of size 2, right? Of cost 2. So EI, it has cost 2. I'm doing this so that I can rule out this one here, because this can never now be used anymore. It would create a circuit. Okay, more of cost 2 that I can do. Yes, I see this one. I'm going to do this one here. So that is DP. No. DP. There's another of cost 2 that I can do. Just I see it here. PL. And this again rules out this one, because that would create a circuit. Okay, can I do still cost 2? Yeah, there's still quite a lot of cost 2, so I'm going to take this one here, MN. Oh. MN, cost 2. There's another one, let's do, oh, I have to be careful now. Look, there's another one, I was thinking of taking this one here, but that creates a circuit, see? So as I said, sometimes these circuits are harder to see because as the graphs become bigger, you might have bigger circuits of larger length and they're harder to recognize. So actually this 2 is out. But there is another 2 that I can take. I see this one here. Okay, that is NO. Equals 2. This again rules out taking this edge because it would create a circuit, right? Yes, it would create a circuit. Anything else? Yes, I see another cost 2. There's a cost 2 here still that I can take. GH. I see another one here. EF. Oops. EF also is cost 2. And that rules out quite a lot here because now this would create a circuit, this would create a circuit, and this would create a circuit. So I don't even have to look at those anymore. And there are no 2's left. The ones that I have not used, these 2 are already unacceptable because they create circuits. So I have to start looking for 3 of cost 3, and I see one here of cost 3. This one, well, doesn't matter. I'll take this one. FJ. That rules out this one. It also rules out this one, by the way, because again, it's harder to see, but this actually is a circuit, right? So I have to rule that one out. There's another cost 3 that I see here, that is KL. But what about the next cost 3 that I can take? This one. But if you now look at it, it's quite a long circuit, but it is a circuit. So that is something, therefore, I cannot take. There are therefore not many left. There are these 4 ones here. Let's see, is there any one of those that I can take? If I would take this one, I would create this circuit. If I take this one, yeah, this would be this circuit, right? And this one would create also a circuit. I have to think a little bit, but I think that's one circuit here. So I think I cannot take anything else anymore. Now, let me verify. Do I have enough? Right. So we normally also should number these. I didn't do this, but let me do this here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's better to do this. I forgot to kind of do this. Because how many vertices there are? Well, 4, 4, 4, 4, so 16. So I know that a tree, to get a tree, the number of edges should be 50. So this is exactly the number that I have, and therefore I'm done. And this also tells me the total cost. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 28. All right? Okay, that's not so hard. And then the next question that I asked you was the number 14. And that involves, that's this one here, the number 3 here, so let me write it here. So number 14 here. No, let me not do it that way. Let me just enlarge this guy. Ignore the top one here, it's the bottom one. So in number 14, let me write it here, let me erase this here. In number 14, what we need to do is find the maximum spanning tree. Now, I did mention it in the lecture, but I didn't say exactly how to do it, so I'm going to quickly go over it. I'm going to use the Kruskal approach. And so what we do, what was the original Kruskal was, the Kruskal approach, you do exactly the same as this in the Prim algorithm, except you ignore the adjacency question. You just look for a minimal cost without making a circuit. And then what we have seen, what you, instead of creating in the Prim algorithm, you're creating at any time you have a tree, okay, a connected tree. In the Kruskal algorithm, what you're creating is a forest that at the very end will become one single tree. Okay, that's the difference. So, but that gives you the minimal cost. So what minimum spanning tree? What will be the maximum spanning tree? Well, it's very simple. Instead of taking the minimal cost, you take the maximal cost. So So let me write it here. So I'm gonna, this repeats now, becomes maximal. That is what I'm gonna do now. I'm not gonna write it up again. It's simple enough to keep in mind. Now let's set up our table here. So we're gonna have a table, right? So this will be the edge and the cost of the edge and the number of edges. So we have 9 vertices. So the number of vertices is 9. So this is number we're dealing with. So not this one, right? We're dealing with number 3 here. Okay. So 9 vertices. So for a tree, I need 8 edges. The number of edges should be 8. So I can already put them on. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what we need to do is just simply take the highest one available. We see that the values here are costs are between 1 and 8. If I see it well, yes, between 1 and 8. So let's start with the highest one that I can pick, that is 8. I'll make it again a green tree. So I'm picking this one, DH. Remember, we're trying to make a maximum now, so that's why we're always looking for the biggest possible value, 8. Okay, the next value that I can take, there's no 8 anymore, but this is 7, so I'm going to take this. And it happens to connect, but that is not something that I'm worried about. Then there's a 6, there are 2 6s here. I can pick whichever I want, and to just be a little bit, I want to take the other 6. I could take that one 6 and I would still have 1 3, but I want to show you that most likely you're going to get a forest in while you're building this tree. So BF as value 6. Okay, but look, there's not much you cannot avoid certain things, and now I have to take that 6. So okay, I'm gonna have to take the 6 anyway. So DG, and that takes care of the 6s. Okay, let's see with the 5s. There's only one 5, and it doesn't cause any problem. So I'm gonna take it. So AB is 5. There's another 5 I can take. Now it connects already 2 vertices that are part of the forest, but there are different trees, so I don't create a circuit. Okay, so this is when you're connecting, when you have when in this algorithm you're connecting 2 vertices that already are part of your forest. Then if you have to add that edge, there's only one thing you have to check. If they belong to different trees, you're not making a circuit. If they belong to the same tree, you make a circuit. Okay, so that's very easy to see whether you're a circuit or not. Much easier, therefore, in some sense, than in the previous case. Okay, so that was BE that I took, right? BE has cost 5. Here's another one with cost 5. No, now it cost 4 comes. Now I see there is one that I cannot take here. This one would create a circuit. Okay. There's actually another one. This one here, also would create a circuit, right? Because now look, I have only 1 tree now. The 2 trees have been combined. So whenever I connect 2 vertices that lie on the same green line, I will create a circuit. So I cannot do that. So 4 will be out. This 4 will be out too. So I have only really one choice left, and that is this one here, Fi. Fi 4. Now notice we have only one more to choose. There are no 4s left anymore. There are 3s. Can I take a 3? Well, notice that you cannot take this tree here because that would create a circuit. Neither can you take this tree, but the last tree is still available, and so I'm gonna have to take. Oh, there's a 4 still. Oh! I didn't see the top 4. There's a 4 here. That's the one I have to take. I'm sorry. BC. So BC, that is 4. Okay. And now you can verify nothing you can add anymore because it always will create a circuit simply because you have a tree now. With the whenever you have a tree and you connect 2 of its edges, 2 of its vertices, you create a circuit. Simply because you added 1 edge and then therefore there are more edges than they're supposed to be, so it's no longer a tree. Okay, so what does it add up to? 15, 21, 27, 37, 41, 45. Okay, And the minimum one, what was the minimal value here? So you see this is, of course, in question 3, you were asked to do the minimum one. Let me quickly check here what that would have been. Sorry, give me a sec. I'm not going to solve it. I just want to show you that this was number 3, I said. Number 3. That would... Oh, it doesn't tell me what the cost is. Oh, stupid people. Okay, anyways, you have done it, so you know what it is. Okay, so this is quite straightforward and easy, and we'll do a quiz on it, so it makes it easy for you. Probably a little bit more complicated, a bit more this type of graph, a little bit more things to do, and I'll leave it up to you, I think, whether you can use Prim or Quaskle, or I'll see how I do the quiz, but I'll do also a review for it.